welcome back. In this lecture, I will be discussing theories of solution. So, okay, so what is the aim of solution theory? So, basically, if you already seen some of those theories such as Margulis equation, that is one such solution theory. Similarly, we will discuss a little bit more about others, but there is a fundamental way it has been derived, and all of them have the similar aim. Okay, the aim is basically to predict the numerical values of activity coefficient in terms of properties or some kind of constants which must have some physical significance or physical property associated with it. Okay. So, the properties which are related to activity coefficient should have some physical significance, and should be, or rather preferably be computed from pure component properties. Okay. So, this is basically the major aim of solution theory. Of course, there are various different theories which we will see or exist in today's set of solution theories. Now, you can segregate these kind of theories in two forms, one which has a basis of physical interactions, okay. So, I can differentiate the theories based on the concept of physical interaction, other is based on chemical in nature, chemical interactions such as like bonding and solvation. So, within this type of theories, you have other kind of sub topics such as association, which are theories which are based on associating nature of the fluid, solvation. So, within solvation you can have ideal solution of complexes, and this is another one is Harris theory. Okay. And in case of association, you have basically divided into two parts. One is basically association, and other again you can have a solvation kind of concept in that. We are not going to discuss chemical type of theories. Okay, it's altogether exhaustive analysis, and I would like to avoid that. We can just focus on the theories which are physical type, and Margulis was one of the example which we have looked into earlier. So, here you can have many different theories: Van Laer, Scatchard, Hildebrand, and there is a large set of theories which are based on lattice theories. Then you have corresponding state. Okay. And then you have this another one which is a Scott, okay, and Renon, NRTL, non-random is one of the example, NRTL. And lattice theory has many different possibilities of the different theories which has come up with. So, Margulis is one, then this Guggenheim, then this Fleury-Huggins, and this Wilson. Okay. Now, as you can see that it is exhaustive in terms of the number of theories, and of course, I cannot cover everything within this theories of solution, but what we can do is we can illustrate one or two theories to get an idea how it has been derived. And so, one of the two popular theories which we are going to look at is Van Laer and particularly Scatchard Hildebrand, and later on I am going to discuss the polymer solution. There I will look into the Fleury-Huggins theories. Okay. So, let me start with the Van Laer theory. Okay. So, consider let us say x1 moles mole fraction of liquid 1 and x2 of liquid 2. Okay. And what we are assuming in this case as far as Van Laer is concerned is the two liquid which has liquid 1 and liquid 2 mixes at constant temperature and pressure such that excess volume 0, that is there is no change or there is no volume change, and SE excess entropy is 0, that is entropy of mixing is 0, which corresponds to ideal solution. Okay. Okay, so in such case at constant P we can consider G of E as U plus PV minus TS. Since is excess E, I am going to put here. Now, with this assumption, this is going to be 0, this is going to be 0. So, therefore, GE is equal to UE. Okay. And UE in this case would be nothing but delta U, change in U when two liquids are mixed at temperature and pressure. So, let us first consider how this mixing would be thermodynamically path can be considered for this particular mixing of two liquids. Okay, so, we will be looking at three different stages where we can bring the liquid from almost idle gas, mix the idle gas, and then later on compress it to the liquid. So, that will become the liquid mixture. So, let me just schematically represent that in order to explain it. So, you have two liquids. Okay. So, let us say this is at P and T. Okay. Both are at P and T. All right. And you take this liquid 1 to extremely small pressure, keeping the temperature constant, making it to be idle gas. Okay. And then you mix both this liquid 1 and 2, which are now idle gas at very low pressure, pressure goes to almost 0. That means you are vaporizing each pure liquid at constant temperature or expand. and I am going to represent this as I1, first path 2, and here we are going to mix it somewhere here. So, this is mixing occur. So, mix ideal gas. Okay. So, this is 2, mixing is 2, this is again at 0 to keeping temperature T, and then from here we are going to compress it. So, you compress or liquefy this gas mixture at constant temperature, that means isothermally, and this I am going to define as third path to get the liquid mixture at P and T. Now, in this process, what is the change in the or what is the basically G axis or U axis or delta U? So, U axis or delta U is going to be the mixing of here in this path, that is from P t to P equal to 0 T. Okay, so, I am going to add this, and since it has x1 moles fraction, or in general we can weight these changes in the energy. So, this is x1 times delta U 1 that means this one, okay, plus x2 delta U of this path plus delta U for this mixing of the ideal gas plus delta U of this path. Okay, so, you have this component which you need to evaluate in order to get U axis. Okay. So, what I am going to do now next is let us consider step 1. Okay. So, step 1 was to vaporize isothermally So, let us consider the basic relations of the partial derivative of internal energy with respect to the volume at constant temperature is nothing but this. So, this you can show, okay. You have done this kind of exercises earlier in the course. So, we use this because at the end what we are doing is we are changing the volume because we are expanding. So, we need the change in the internal energy with respect to the change in the volume, and that is related to the partial derivative of the pressure and temperature. Now, at this point you need some kind of equational state, and this is where Van Laer unfortunately took the van der Waal equational state. Okay. So, if you consider van der Waal equation of state, and if you are wondering why he had to take the van der Waal equation of state, because Van Laer was a collaborator of van der Waal. So, if you use this equation of state, then this particular expression will turn out to be A by V square. Okay. Now, you can integrate this delta U, U ideal minus U of the first liquid is going to be V L1 infinity, A1 indicate that is basically liquid 1, okay, and this is going to be A, this is going to be A by V1 L. Okay. So, this is the expression of delta U. So, this will be your delta U. Now, similarly you can get for delta U I2, that will be your A2 V2 L. Okay. Now, you need this term which will be your delta U1, that is combining this both vaporization of the liquid. Now, I can combine this, therefore, delta U1 is A1 V1 L x1 plus A2 V2 L and x2. Now, according to the van der Waal theory, molar volume of liquid below T such that, or at T such that T is much less than Tc, then the molar volume at T can be replaced by B. Okay. So, considering that, I can now write this expression okay. So, this is for delta U1. What about delta U2, which is basically corresponding to the isothermal mixing of gases at low pressure, that is basically nothing but ideal gas. So, ideal gas mixing at constant temperature, the changes in the internal energy should be nothing but 0. Okay. So, now what remains is basically the third part, which is this. So, here we are going to compress it from low pressure to the pressure of the system, okay. And in a similar way as we have done, we will be using this, okay, but instead of V1 infinite V1 to infinity, it will be infinity to V, and A will be now A mix and V mix. So, let me just write down here. So, third step 3 is basically ideal gas. So, this is step 2. Ideal gas mixture is compressed isothermally and condensed at the original pressure. Okay. So, delta U3 is infinity to V L will be del U mix divided by del V at T dV, and this is nothing but minus A of mix divided by B of mix. Okay. We may not know at this point, okay, that the effective A and B of the mixture. So, this is what is going to be delta U mix. Okay. Now, van der Waal of course has worked on this, and he has defined this A mix in terms of the pure component. So, this is x1 square A1 plus x2 square A2 plus 2 x1 x2 A1 A2. Okay. So, this is nothing but A12, and so A12 is considered to be the geometric mean of A11 and A12. So, that is A1 multiplied by A2. Okay. So, that means here only interaction between the 1 and 2 is important. Now, on the other hand, B mix is simply considered as a weighted average of the sizes x1, x2, B2. That means there is no volume change upon mixing. Therefore, no volume change upon mixing. Okay. Now, with this information, okay, you can plug all this back in this expression, and since U xs is nothing but G xs, I can rearrange this data and obtain Ge in terms of x1 x2 b1 b2 x1 b1 plus x2 b2. Okay. So, this is A divided by b1 minus A2 divided by b2 square. Okay. So, this is the expression which comes out after coming up with this simplifications of the expression by plugging in all this different parts which we have calculated back in u axis, okay, and then using the fact that the g axis is nothing but u axis. Now, given that you have obtained the value of g axis, now you can connect this to the activity coefficient. Okay. So, that is that you may like directly use this expression here. Okay. So, this is the total number of moles multiplied by G E here. So, with this you should be able to obtain for the binary mixture the expression which we have written without going through the detailed derivation earlier in the lecture. And this is nothing but the 2 parameter model. Okay. So, this is for the log gamma 1 and this is log gamma 2. And what is A and B? So, A dash is given by B 1 by R T square, whereas B dash is B 2 by R T. Again the terms are same as in the case of A 1. Okay. So, this is a positive value, B is a positive, thus A dash and B dash in this they are positive. Okay. But this is important that this is proportional to 1 by T, okay, for both the cases. Considering this, you can summarize or you note the following points, that log of gamma I is proportional to 1 by T, and as we have discussed in the last lecture that this is essentially indicative of that x is 0. The second point is that both the cases log I is greater than or equal to 0, which essentially means that gamma I is greater than equal to 1. Okay. So, log gamma I is greater than or equal to 0 is directly from here, okay, that this is a positive value, and that is why it is greater than or equal to 0, which indicates this, and this is nothing but implies when gamma is greater than 1, it is a positive deviation from the Raoult's law. Okay. So, this implies this is a positive deviation from Raoult's law. Okay. So, you should also note here that A mix which we have considered here, okay, A mix here, this A mix, the expression which we have used is less than x 1 A 1 plus x 2 A 2. Okay. So, and remember this, what is A is basically nothing but is a proportional to the forces between the molecules. So, it tells you, this expression tells you that the forces of attraction between molecules in mixture is less than they would have been if they were added in additive on molecular or molar basis. Okay, is less than the, you know, if they were added in a molar basis. Okay. So, assume that if Van Laar had taken the following, okay, this would have implied that in such case you would have got this for all values of x. Okay. So, which would have been this a negative deviation, but since it took on this essentially this model, this assumption, that is why you are getting the positive deviations, and for gamma equal to 1 you know that would be your ideal solution. So, the difference is mainly you know, the assumption is mainly because of this assumption of A mix, and for that you are getting a specific kind of behavior using this kind of theory. Okay. Now, there is certain salient features of Van Laar theory. This is something which is important to note. So, Van Laar theory basically relates non-ideality to critical pressure of the pure component. Okay. So, according to van der Waals equation of state, P c of I is proportional to the root of A by B. So, Van Laar theory says that the non-ideality of solution increases with the difference between the pure components P c increases. Okay. So, therefore, if delta P c is 0, which means we would expect to be ideal behavior, okay, but this is contrary to experimental observation, okay, and thus you can clearly see there is a flaw in the van der Waals, or there is a flaw in Van Laar's theory. So, one of the basic reasons for this is the usage of van der Waals equation of state. Okay. So, that was a major problem, and many theories came out later which try to remove this kind of obstruction. So, one of the common theory which has done that is basically Scatchard-Hindelburg theory, and that is something which I am going to discuss in the next lecture. So, that will be it for this. See you in the next lecture.